Hello everyone and welcome to Physimania. In today's video, we're going to do the third class for cosmology in this series of lectures that I'm doing. So without further ado, let's get started. Let's look at the content that we're going to go through today and hope you enjoy it. All right, so the content for today is going to be first, we're going to look at the relationship between C, so the redshift C and the scalar factor A. So we're going to find that relationship. Then we're going to be deriving the first Friedman equation, which I'm just going to denote by this F1. So Friedman equation. And third, we're going to derive the second Friedman equation, okay? So this F2, which I might write as this Fi or F1, or same thing for the second Friedman equation, okay? Either F double I or F2. All right, so let us start by looking at the relationship between the redshift Z and the scalar factor A. And so to start with this, okay, we have to remember what is the distance that light travels, okay, which is what we saw before, and this is what we know as the coordinate distance or the conformal distance as well. And so remember, this was given by this chi parameter, which is dependent on time, okay? And it's going to be basically given by the speed of light times the integration from some time t all the way to some t naught, which is kind of like the observation time for this light, or like this light that we are observing at a specific time. And then the integrand is going to be dt prime divided by the scalar factor evaluated at t prime as well. Okay. And so this is our starting point to try to find this relationship. Okay, so what we're going to also consider right now is that we have a light that is going to be emitted at a specific time TE, okay? So light emitted at time equals TE, okay? And so it travels to us from a specific position in the sky, and it reaches to us at a specific time T naught, okay? So we observe it at a specific time T naught. So what we're going to have is then that this coordinate, this conformal distance, okay, is going to be given by C, and then it's going to be the integral from TE, okay, from the time emitted to the time of observation, times dt prime over AT prime, okay? And so T naught again is time of observation. And so now what I want you to consider is whichever object has emitted this light, okay, this wavelength of light, right? As soon as it emits this first wavelength of the photon of this light ray, then it's going to emit another light ray, right? And when is this going to happen? When is it going to emit? At what time is going to emit this second light ray that we're going to be able to observe? It's going to be emitted right after it has finished emitting the first one, right? And so because it has some wavelength, which we're going to call wavelength E, wavelength E, and then it's traveling at the speed of light, then the second light ray is going to be emitted at time equals of TE plus lambda E over the speed of light, right? So imagine if you have, let's say, you have the sun, for example, right, which is emitting a light ray, okay? It's not going to emit the second light ray until the full wavelength of the first light ray has been emitted. And so that if you have a wavelength lambda E to begin with, then this second light ray, okay, this second light ray, which comes right after the first one here, this second light ray, which comes after the second one, is not going to be emitted until you have a specific time, which is going to be the wavelength over the speed of light, because that's the speed at which is going out of the sun. Until that time has not passed, then we will not have the second light ray being emitted. Okay, so with this said, then this means that when the light rate, when the second light rate is going to arrive to us, is going to be at some time t naught plus a wavelength which is going to be given by the wavelength that we observe divided by the speed of light. And in this case, remember, we have the universe which is expanding, so the wavelength that is going to arrive to us is going to be bigger than the wavelength that was emitted by the actual star, okay, or galaxy or whatever. So in this case, second light ray, which is emitted at this time, TE plus lambda E over C, and then observed at T equals T naught plus lambda naught divided by C, okay? Because again, it has a different wavelength once it has arrived to us. And this means that this second light rate, we can also find what the conformal distance for this second light rate is going to be, which is going to be C, and then TE plus lambda E over C, and T naught plus lambda naught over C. And then the integrand, same thing, okay? But you have to remember that this conformal distance is going to be the same, because the path that the first light ray and the second light ray have to travel is going to be the same, okay? Which means now, in order for us to be able to start finding the relationship between A and C, what we're going to do next is actually going to be making equal both of those paths, right? So these two these two conformal distances that we found, we know they have to be the same. So we are just going to get what we have on the right hand side for both of them, and then we're going to make them equal to each other. And then we see that the speed of light is going to cancel out. And what we can do next is, on the right hand side, we can rewrite this integral in terms of three more integrals, right? And so remember, we have different different limits in the integration variable, so we can use that and use our tricks of calculus to be able to make our life simpler. And you'll see what I mean right now. So what I mean right now is, what we're going to have is, on the right hand side, is we're going to have first an integral that goes from t emitted to the observed time, plus then an integral that goes from t naught all the way to t naught plus lambda naught over c. And so if you realize, if we were to make these two integrals equal, or like make it equal to 1, we can. And this is because, since the limit of integration is repeating here and here, then in reality, the only two limits of integrations that we care about is going to be this one and this one, okay? But again, we don't have this TE on the right hand side. We have TE plus lambda E over C. So what we want to make sure is, now we include another one to make sure that we are getting rid of the of the terms that we in reality we don't care about. So this is kind of like adding 0, okay, to an equation. So we have this one which will cancel out with this one will cancel out with this one, and at the end of the day we will just end up getting the same limits of integrations that we had in the equation above, okay? And this is true because our integrand is not going to change also between integrals, right? And so what do we have right now? What do we see? What we see is now that we can now cancel out this integral that we have right here, okay, the first one in the three integrals, with the one on the left hand side. And what this means for us then is, we can now pass, for example, we're going to leave, yeah, we're going to pass this one to the left-hand side. And what we're going to be obtaining is the integral between TE and TE plus lambda E over C of dt prime over AT prime is going to be equals to the integral between T naught to T naught plus T naught lambda naught over C times dt over AT prime, okay? All right, so that's the result that we get for now, okay? We now have to evaluate what this integral is going to look like, okay? And so also note that when I'm passing this one to the other side, I pick up a negative sign. But because I have a negative sign, then I can flip the order in the limit of integration, okay? This is just a standard calculus trick. Let me know if this was confusing. I'll try to explain what I mean with some other examples. All right, so what we're going to do now to try to evaluate these two integrals that we have here, to try to find that relationship between A and the redshift, which right now we are like, where is the redshift coming from? We still don't see it, but at some point, because we have these wavelengths, you'll be able to see that we can actually bring out the redshift. But for now, just bear with me and we'll go through it. So what we're going to do now is we're going to guess that the scale factor goes or can be written as a power law, okay? For example, this t to a polynomial of order n. And we're going to guess now what we should be expecting in our answer, okay? And so let's do it just generally. We're going to have some time and then a time plus a wavelength over the speed of light. And then our integrand is going to become dt prime times t to the negative n. And what this means is that we're going to get t to the negative n plus 1 divided by negative n plus 1. And this has to be evaluated at the limits of t all the way to t plus lambda over c. All right. And then what we end up finding once we apply the limits is 1 divided by 1 minus n times t t raised to the power of minus n plus 1 minus t plus lambda over c raised to the power of negative 1 plus 1. Okay, and what we're going to do next is now we're going to factor out one of these. What we're going to factor out the t's, okay? And what we are going to end up finding, so again, here we have t plus lambda over c. What we're going to end up finding is the following. We're going to have t negative n plus 1 divided by 1 minus n. And then we're going to have 1 minus 1 plus lambda over c times t, negative n plus 1, okay? And so if you realize, then in this term that we have here, the one that I'm marking is that we have a wavelength, okay, which is going to be the wavelength of light. And in this case, it can be, I don't know, in the visible range, X-ray, infrared, whatever you want. But then we have the speed of light times time, okay? And so as you can guess, the speed of light is much, or this distance that we get between c times t is going to be a distance that is very, very large, okay, compared with lambda. So what we can do is now actually approximate this term that we have here in terms of exponential using a Taylor series expansion. And so what we are going to end up finding is basically the following, okay? This is now going to be an approximation, but this is going to be t minus n plus 1 divided 1 minus n. And then in parentheses, we're going to have 1 minus 1 plus 1 minus n times lambda over c times t. And so as you can see, now these factors of 1 are going to cancel out. Then this 1 minus n is going to cancel out with the one that we have outside. And then this t is going to cancel out with this one. And so what we are going to end up finding is basically that this integral can be approximated as lambda over c times 1 over the scale factor. And so remember, this is true since we were saying that the scale factor is going to go as a power law, as t to the power of n. And so what this means for us is that we were only staying with t to the negative n. So that means 1 over the factor of 1 over the scalar factor, right? And so this is our solution to this integral. Okay, so this means that if we apply it to this equality that we have here, then what we are going to end up finding is going to be lambda emitted divided by the speed of light times 1 over the scale factor at the time emitted equals to lambda observed over the speed of light times 1 over the scale factor at the speed 1 over the scale factor evaluated at t naught. Okay, now so obviously the the speed of light is going to cancel out, and then what we're going to get is going to be lambda at time observed divided by lambda at time emitted is going to be lambda observed divided by lambda emitted. And so if we now bring the definition of the redshift, which is C is going to be lambda observed minus lambda emitted divided by lambda emitted, which can be expressed as lambda observed over lambda emitted minus 1. This means that the ratio of lambda observed over lambda emitted is going to be C plus 1. And what we're going to finally get is the relationship between the scalar factor and the redshift, which in this case is going to be A at time observed divided by A at time emitted is going to be equals to C plus 1. And if you remember, okay, I think I've said this in previous videos, at every time of observation means is or present. So this means that lambda t naught is actually going to be given as 1, because this is kind of like a normalization that we do in cosmology. So basically we always say that that the scale factor evaluated at the time observed is going to be equals to 1, which means then that A as a function of t, or at any given time, which was emitted, is going to be given by 1 divided by 1 plus c, okay? And so this is basically the relationship between the scale factor, and in this case here it will be as a function of redshift. But basically the relationship now between the scalar factor and redshift is going to be given by this equation that I'm showing you right here, okay? Okay. So let us follow with the derivation of the first Friedman equation, okay, of Fi. And we're going to be doing, so this can be done in two ways, basically. The first way is going to be by just going straight to general relativity, okay, the theory of relativity from Einstein, and then doing all of the equations. This is going to be kind of like hard. So this is not what we're going to do. This is not the approach that we're going to take. But please let me know if you think this is something that I should do, and I'll be happy to do it. So what we're going to actually do is go to a simpler model of Newtonian physics, where we can actually also derive the same solutions, or almost the same solutions as with general relativity. Now, there was a joke actually by a professor at Stanford, actually on some YouTube video from the cosmology class at Stanford. And the guy will joke about saying that if Newton had been smart enough, then he would have been able to actually also find this type of equations for our universe. But you know, he was not smart enough, so somebody else had to do it for him. All right, so jokes aside, okay, let us start again by using Newtonian physics. And what we're going to do is we're going to start by assuming a sphere which is pressureless, okay, because it's going to made of matter. What we're going to have is that this sphere is going to have a physical distance given by this RST. Is going to have a mass, which is going to be given by 4 pi divided by 3 times the energy density as a function of time times RST to the cube. And now what we're going to do next is actually we're going to start by using the second law from the Newton's second law, which what is going to tell us if we use it in combination with Newton's law of gravity is the following. So we're going to have basically that the Newton's law of gravity is going to be G times the mass of the sphere times a test mass of a particle divided by the radius square at which, and we're going to assume that this test particle is going to be at the same distance as the mass of this sphere. Okay, and so using Newton's second law now, then this tells us that we're going to have the second derivative with respect to the radius, okay, which is going to be obviously the acceleration. And this is going to be equals to the right-hand side on this equation, which is going to be negative G times the mass of the sphere times the mass of the test particle divided by R squared. The masses are going to cancel out, and what we're going to end up finding is just this equation which relates or acceleration to the radius or the inverse square radius of this sphere. And what we are going to do now to try to solve this this is kind of like a differential equation, okay? So what we're going to do to try to find this a solution for this differential equation is going to use a trick that we use in physics, and which basically is going to go from having a second order differential equation to have a first order differential equation. What we're going to do is we're going to multiply both sides by the derivative of this radius with respect to time. And what we're going to obtain is the following. And then we're going to integrate all of these. So then we're going to have the integral with respect to time of drs dt times this second rs dt second equals to the negative of the integral of g times dt times the mass of the sphere divided by the radius of the sphere square times times dr s dt. And so if we pay attention now to this left-hand side, this can actually be written in terms of something that allows us to automatically evaluate what the integral is going to be. And this is the following. This is actually going to be the derivative with respect to time of the derivative with respect to the radius to the square, okay? And this is true, okay? And actually this is going to be a half right here. And this is going to be true because now we're going to have 1/2 if we apply the derivative, okay? So now we're going to have 1/2 times 2 times dr dt times the second derivative with respect to the radius of this radius with respect to time, okay? So as you can see, it's the same thing that we have right here, except now we have to, we can just simply evaluate the integral because the dt's are going to cancel out. And so we're going to obtain the result that we have, that we want, which is a first order differential equation, okay? And likewise, so actually on the right hand side, then the dt's are going to cancel out. And so now what we actually going to have is an integral, because this dr is not going to disappear, right? So we're going to have an integral with respect to the radius, but again, it's very simple to solve this integral because this r2 will pass to the top as r to the -2, and then we just have to apply the regular integral rule, which is just the power that you have plus 1 and then divide by the same thing. And so what we end up finding for this integral is the following, is we're going to have 1/2 of drs dt squared being equals to Gm divided by Rs, just Rs, plus an integration constant, okay? A constant that comes from integration, which is this E that we have right here. Now, as I said before, this radius is actually given in terms of the physical distance. And what we can do now is actually relate this physical distance to the moving distance, okay, via the scale factor, okay? So if you remember, then any physical distance can be related to the moving distance via the scale factor by just simply multiplying the scale factor times the moving distance, which in this case we're going to denote with this Rs, okay? And therefore what happens now is that all the time dependence is going to be encoded into this scale factor. And so if we take the derivative with respect to this distance, then only the scale factor is going to take this derivative. And so we can do the same thing for the mass of the sphere and the radius of the sphere here. And what we're going to end up finding is 4 pi over 3. And then this was given in terms of the density, energy density times r to the cube, which means that if we divide it by Rs, then what we're going to find on the top is going to be just the square. And so this is going to be, and so this is the ratio between Rs and Ms. Let me just write it a little bit more neatly, okay? Okay, so now evaluating this, this ratio, what we end up finding is basically 4 pi over 3 rho of t, and then this is going to be a square of t times Rs square, okay? Which means that these first order differential equations that we had, now we can evaluate it very simple in terms of scalar factors. And what we're going to have is 1/2 a dot square times Rs square being equal to 4 pi over 3 g times rho times a square times Rs square plus e. Okay, and what we're going to do now to find the expression that is commonly used, one of the expressions actually, because we'll see there's actually one or two more expressions that we can find from this same equation, which are going to be the same thing, is just expressed differently. Uh, one of the common equations that we can find is, now we're going to divide both sides by this term. So basically we're going to divide both sides by a squared and Rs squared. And what we're going to end up finding, and then we're also going to multiply by 2, okay? Because we want to get rid of this factor here. What we're going to do is now obtain a dot squared divided by a squared being equal to a pi over 3 times g times the energy density plus 2 times the energy divided by a square times Rs square, okay? And this is what we define, or what we derived as the first Friedman equation, okay? This is F1. All right, so it is also worth stopping by for a moment and checking exactly what this equation is kind of like telling us, okay? And so if you realize, right, this term right here is kind of like, it can be expressed basically as the total energy of a system. This term right here can also be thought as the potential energy of a system, and then this one can be thought of as a kinetic energy term, okay? Might be easier to see it when we look at it from this point of view, okay? Where you can see exactly this has like the form of a potential energy term, where we have 1/2 and then we have a velocity term. Then this is exactly a potential energy, and then this is just or total energy, okay? So what is this telling us, right? What is this telling us about our universe, about how it should work, how it has to work, okay? And what this is telling us, okay, basically is, so if we have already a universe which is expanding, okay, this means that for a universe that is already expanding, then a of t must be greater than 0, okay? And so if we now have that the energy of the universe or this system is also greater than 0, okay? And so if we now have E greater than 0, then what this means for us is that our universe, okay, or it basically means one is that the change in rate of the scalar factor, which is basically kind of like a velocity, can never be 0, because otherwise then this term, if we pass it to the other side, is going to be negative, and then on energy has to be greater than 0. Because this is going to be negative, then this means that we have a contradiction. So that's the first thing. It means that it cannot go to 0, okay? And then this also means that this term has to be either greater than 0 or less than 0, okay? So this is like an implication. This is an implication. Either a dot is greater than 0 or a dot is less than 0. And this basically is telling us about whether the universe is expanding in an accelerated way or whether it's collapsing into itself. And if it's negative, then it will be collapsing. And if it's positive, then it will not be collapse. It will be like expanding, right? Now, since the universe for us still has not collapsed and we're not seeing our galaxies recede towards us, then this basically is telling us that we should assume that our universe must be expanding, okay? This is one of the implications. Now, what happens when the energy then is equal to 0, okay? When we have an energy that is equal to 0, then in essence, this will be telling us the minimum velocity or the minimum, or it's kind of like escape velocity, right? It will be telling us what is the minimum change in the scale factor that we need in order to find a universe which is not going to collapse, okay? Basically, we will be able to solve for this a dot and then basically find kind of like a velocity that tells us when the minimum rate of change of the scale factor in order for the universe not to collapse. And then finally, the last case will be if we have the energy being less than 0, okay? Then in this case, the potential energy will keep increasing until it reaches an asymptotic limit, which is going to be a this a dot reaching equal to 0, at which point then the universe will actually start collapsing onto itself, right? So basically, because the energy is negative, then this means this term here must dominate at some point, and even if you start expanding, then it will reach this point at which the a dot is going to reach 0, and then it will just go back and and the universe will basically start collapsing onto itself. So basically, this is kind of like what this first Friedman equation is telling us, which is we can have three scenarios for a universe, and the most likely for us right now is going to be the first one, where we have a universe with energy greater than 0, and then or a system which has an energy greater than 0, and then this a dot is going to be kind of like expanding, okay? This is kind of like the assumption right now for cosmology. All right. Again, yeah, we said we can express this equation in terms of we can re-express it in terms of other things, okay? But first, let me just tell you what actually we find when we use general relativity, okay? When we use general relativity, then this term actually here becomes a term that actually accounts for the curvature of a space itself. So basically, it's an energy that comes from the space itself, from the vacuum itself. And what we end up finding is we have the same thing on the left hand side, which is a dot over a to the square, then a 8 pi over 3 times g times rho minus kappa, which is going to be the curvature. And as you remember from previous videos, then we saw that the curvature can be either 0, 1, or -1. And then this is going to be divided by rs squared times a squared, okay? So basically the same factors that we found here, but now with a kappa. Then this expression can actually be expressed in terms of just energy densities. And let me just show you that right now. So the way that we can actually express this is by having 8 pi over 3 times g, and then this is going to be times rho, the regular rho, plus a rho, an energy density, which comes from curvature, which means that we have defined this rho as -3 divided by 8 pi over g times the curvature parameter times the radius squared times the scale factor squared. All right. Now, there is something that is also going to be very important as we go on to try to understand some other parameters that we're going to define, and this is known as the critical density. Okay. And what is the what is the critical density? The critical density is going to be basically an energy density that we're going to define when our universe is flat. So basically when kappa is equal to 0, then from this first Friedman equation, we are actually able to find what we define as the critical density, okay? So if we have kappa equal to 0, then this term disappears, and then we only have these two terms. Then we only have to solve for this rho, and this is going to be what we're going to define as the rho critical, which then is given as rho critical as a function of time being defined as a dot over a squared times 3 divided by 8 by g. And so if you realize, if you remember from previous lectures or from the last video, then we actually define this ratio between a and between a dot and a as the Hubble parameter, which means that we can just simply write this as 3h squared divided by a pi over g, okay? And this is basically what we find the critical density. And this now actually allows us to introduce a new parameter, which is what we call in cosmology simply omega. So as you can see, not very good with names, but this omega, okay, is going to be defined always as the ratio between the energy density to the critical energy density. And given this omega, then now what we can actually do is rewrite the first Friedman equation in terms of the omega. Okay, so remember, Friedman equation is just h to the t squared, a by g over 3 times rho minus kappa, then divided by r squared times a squared. Okay, and what we will do next is then we're going to divide both sides by the Hubble parameter square, so h squared. And what we're going to end up finding is the following. We're going to have 1 divided by a by g 3h squared times rho minus kappa h squared r squared times a squared. And if you realize, then on the first term here on the right hand side, what we have here is the inverse of the critical density, which means this can just simply be expressed as omega t minus kappa, or sometimes in cosmology, then this actually can also be defined as k divided by h squared over a squared, where the k is simply just the definition of kappa divided by the radius squared, okay? And so this is basically just another way. So I'll put it right here, equal to omega t minus k over h squared over a. This is simply another way of rewriting the first Friedman equation as well. And finally, we're going to arrive to the second Friedman equation, okay? Derivation of Friedman 2. And again, we're just going to simply use Newton's law of gravity, and the second law, the second law of Newton's second law. I'm sorry. And again, this is going to allow us to basically find a result for this second Friedman equation. So again, you see how everything, could have been done from Newton's gravity instead of general relativity, but it's very nice to see how this actually played out in history. All right. So we're going to assume once again that we have a sphere, okay, and then we have a test particle, which is in this sphere at a specific radius. And what we're going to have then is the force of gravity, once again, equals to the negative of g times the mass times the mass of the test particle divided by the radius squared. And now we're going to do the same thing where the radius can be expressed in terms of the co-moving distance as a of t times the co-moving distance, okay, or this co-moving radius. And what we're going to do now on the next side is, this time again, we know that this equation will just give us the second derivative with respect to the radius being equals to the negative of g times m divided by the radius squared. And instead of trying to decrease the order of this differential equation, what we're actually going to do is leave it as a second differential equation. And then we're going to take the second derivative of the physical radius, which again is simply going to give us a dot of t times rs, or this co-moving distance. And then on the other side, what we are actually going to end up finding is negative g over m divided by a of t squared times rs squared. And next, what we will do is we're going to divide both sides by a and by rs. Okay, so we're going to divide these two sides by the scale factor and rs, but only with one power. Okay, so not the raised to the second power, only by one power. So what we'll have is a of t, double dot a as a function of time divided by a being equals to g negative g m divided by a to the cube times rs to the cube. And remember once again that the mass of this sphere can be expressed in terms of the volume, and then also in terms of the energy density. Okay, then this is going to be 4 pi divided by 3 times g times rho times the cube of this radius, which is going to be a to the cube rs to the cube, and then this divided by a to the cube and rs to the cube, which means that this is going to simply cancel out. And then the second Friedman equation now is given by this a double dot divided by a equal to 4 pi over 3 times g times rho. And this is going to be the second Friedman equation using Newton's law, okay, and the second of Newton's law. And so one thing that I do want to mention of this, okay, the one of the assumptions that we have made in order to be able to do this with Newton's gravity, a gravitational law, is that we are assuming that our universe is full of matter, and this is the dominant component of the universe. So basically, even though if we have light, we have any other type of dark energy or whatever, what we are saying is that matter is going to be the dominant component of the universe if we want to reach this conclusion using Newton's law. Otherwise, then we cannot use it. If we assume that we have other components, then we actually have to use general relativity. And so when we use general relativity to try not to assume that the universe is dominant by matter, is not dominated by matter, then what we actually end up finding, okay, so basically in GR, what we end up finding is that the second Friedman equation becomes this A double dot over A equal to negative 4 pi over 3 G times rho plus 3 times this capital letter P, which is actually going to be the pressure done by the fluid that we are saying is dominated or is dominating in the universe, or the combination of different fluids. Okay, so what does this tell us about matter? This is actually also telling us something about matter. Okay, so again, let me just make this into a nice square. But what this is actually telling us about matter is that for matter for matter then the pressure done by matter must actually be equal to 0. Okay, otherwise then it will appear, it will have appeared also in our use of Newton's gravitational law. And so with this, we have basically arrived to the end of this class. Thank you very much for listening in. Please let me know if there's anything that is not clear. And I really hope to see you in the next video, and let's keep learning cosmology together. Thank you. See you soon.